Hello, and welcome to today's lesson on calculating elastic potential energy. Today, we will learn what the spring constant is and how it relates to elastic potential energy. We will also begin to understand how to use the equation elastic potential energy equals 0.5 ke squared and practice applying it to various scenarios. So far, you have become familiar with the concept of elastic potential energy. You understand that it is the energy stored in an object when it is stretched or compressed. Building on this foundation, we can now explore the mathematical representation of elastic potential energy. This lesson will advance our understanding of energy transformations and how they depend on the physical properties of materials. Imagine you're stretching a spring. The more you stretch it, the more effort it takes. This extra effort means more energy is stored in the spring. So when something is stretched or compressed more, it has more elastic potential energy. Not all springs are made equal, though. Think of a rubber band and a metal spring. It takes you more effort to stretch the metal spring than to stretch the band the same amount. This is because the metal spring is stiffer. But how do we measure stiffness? Stiffness is measured by something called the spring constant. The rubber band has a lower spring constant, meaning it's less stiff, while the metal spring has a higher spring constant, meaning it's stiffer. So, the stiffer the material, the harder it is to stretch, and the higher its spring constant. As it takes you more effort to stretch the stiffer spring, this means more energy is stored in it, so it has more elastic potential energy. We would expect the formula to show that the more a spring is stretched, the more elastic potential energy it has, and that stiffer springs, or springs with higher spring constants, store more elastic potential energy. The formula for elastic potential energy, or EPE, is 0.5 times the spring constant, K, times extension squared. It is important to note that the extension can also sometimes be written as x squared. As expected, the formula suggests that as the spring constant or the extension increases, the elastic potential energy also increases. The spring constant is a measure of how stiff or stretchy the spring is, and it is measured in newtons per meter. A higher spring constant means the spring is stiffer. Extension is the distance the spring is stretched or compressed from its natural position, measured in meters. Note that compression and extension are treated the same for energy calculations. Also note that extension isn't the same as the length of the spring. This is a very common mistake. Instead, it's the difference between the spring's original, unstretched length and its length after a force has been applied. It is also worth noting that elastic potential energy, like other energy types, is measured in joules. Let's work through an example. Imagine you have a spring with a spring constant of 50 newtons per meter, and you compress it by 0.2 meters. You want to find out the elastic potential energy stored in the spring when it's compressed. First, identify what's given. The spring constant is 50 newtons per meter, and the compression of the spring is 0.2 meters. Now, identify what we want to find. Here, this is the elastic potential energy stored in the spring. Next, choose the relevant formula that has what we are given and what we want to find out. We'll use the formula elastic potential energy equals 0.5 times spring constant times extension squared. Make sure to check the units are standard units and convert if needed. Here, both are in their standard units of newtons per meter and meters, so we do not have to convert anything. We can now plug the given values into the equation. Elastic potential energy equals 0.5 times 50 times 0.2 squared, which is 0.04. This gives us a final value of 1. Adding our final units leaves us with an answer of 1 joule. So, the elastic potential energy stored in the spring when it's compressed by 0.2 meters with a spring constant of 50 newtons per meter is 1 joule. Understanding this concept helps us see how energy is stored in elastic materials and can be useful in a wide range of applications, from mechanical systems to everyday objects, like rubber bands and trampolines. Let's apply what we've learned to a few specific problems. Calculate the elastic potential energy stored in a spring with a spring constant of 500 newtons per meter. that is stretched by 0.2 meters. First, identify the known quantities. The spring constant equals 500 newtons per meter. Extension equals 0.2 meters. Use the formula. Elastic potential energy equals 0.5 times 500 newtons per meter times 0.2 meters squared. 0.2 squared is 0.04, and 0.5 times 500 is 250, which gives us 250 times 0.04. Doing this calculation leaves us with a final value of 10 joules. So, the elastic potential energy stored in the spring is 10 joules. Let's look at another problem. A spring with a spring constant of 250 newtons per meter is stretched from its original length of 1 meter to a length of 1.3 meters. Calculate the elastic potential energy stored in the spring. First, start by identifying the known quantities. The spring constant is 250 newtons per meter. The original length is 1 meter, and the stretched length is 1.3 meters. In this case, we aren't given the extension, so we need to calculate it by subtracting original length from final length. 1.3 minus 1 gives us a final extension of 0.3 meters. Finally, plug this into the formula. 0.3 squared is 0.09, so we need to do 0.5 times 250 times 0.09. This gives us 125 times 0.09, which finally leaves us with a value of 11.25 joules. Thus, the elastic potential energy stored in the spring is 11.25 joules. Let's look at one final problem. A spring with a spring constant of 300 newtons per meter is compressed from its original length of 0.5 meters to a length of 0.3 meters. Calculate the elastic potential energy stored in the spring. First, start by identifying the known quantities. The spring constant is 300 newtons per meter, the original length is 0.5 meters, and the compressed length is 0.3 meters. Again, we aren't given the compression, but instead we are given lengths. We need to calculate the compression. 0.5 meters minus 0.3 meters gives us a value of 0.2 meters. Lastly, we can now use the formula and plug our values in. 0.2 squared is 0.04, and 0.5 times 300 is 150. 150 times 0.04 leaves us with a final value of 6 joules. By working through these examples, we can see how to properly apply the elastic potential energy formula to different scenarios. In today's lesson, we introduced the formula to calculate elastic potential energy, which is EPE equals 0.5 times the spring constant times the extension squared. We clarified the key quantities involved in this formula: elastic potential energy, measured in joules, spring constant, measured in newtons per meter, and extension, measured in meters. We examined multiple worked examples to solidify our understanding of how to use this formula in calculations. By mastering this formula and recognizing the associated units, we can further our understanding of elastic potential energy, which is crucial for a broader comprehension of energy principles in physics.